regarding bandwidth. Okay. So why I'm not writing a bandwidth? What is the bandwidth of AM? Now see here, this is an AM signal. What is AM signal? DC component added to the message signal multiplied with carrier. This is nothing but amplitude modulated signal. Now which results, the equation is AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT. Now the demodulation is successfully done by envelope detector as bandwidth which is equal to 2 omega and the total power which is equal to carrier power plus upper sideband power plus lower sideband power. Now this is what we are having in AM, right? So what is the bandwidth in AM? The bandwidth in AM is 2 omega. Okay. Now which is high or which is less, which is advantage or which is disadvantage? Now students are immediately saying that, sir, which is an advantage? And some of you are saying that which is a disadvantage. Now one point I am already saying to you, to accommodate more number of signals through a single channel, the main application of the communication techniques is nothing but multiplexing. To transmit more number of signals through a single channel is called as multiplexing. Now if you want to multiplex more number of signals, so the signal bandwidth, the signal is nothing but a modulated signal. The modulated signal bandwidth should be as minimum as possible and the channel bandwidth should be as maximum as possible. In the starting classes itself I am explaining this. For better multiplexing, the modulated signal bandwidth should be as minimum. For better multiplexing, the channel bandwidth should be as maximum as possible. But we are talking about the signals, modulated signals. Therefore, if you want any new modulation technique in your mind, so definitely I am expecting this bandwidth should be less than this one. Okay. So this bandwidth of new modulated signal, the bandwidth of new modulation technique should be expected that which is less than the already the available one. So how I can reduce the bandwidth? So in my mind there are two concepts. So in AM the number of components are carrier and two sidebands. Okay. Now this is this term because of this is coming because of DC term, and this is a carrier component, and there are two sidebands. Okay, upper sideband and lower sideband. Okay, DC term, and this is carrier component. Okay, now what we are doing here is, now this term is coming because of the DC. There are three spectral components: carrier, upper sideband, lower sideband. Now I want to eliminate one component. So out of these three spectral components, if I eliminate only one spectral component, there are two spectral components or not? So carrier, upper sideband, lower sideband. If I eliminate one component, there are two components, such that I may expect that the bandwidth is decreases. Therefore, so to keep that particular point in my mind, so I just remove this term. This term will make it to 0. This term is make it to 0 means now the DC will become 0. When the DC will become 0, what is the AM signal? Now the DC will become 0. Now this AM signal is nothing but, now this is message signal multiplied with carrier. Now which is nothing but, now this is 0. This is 0. So when DC is 0, what happens? Now that effect is first will be on the envelope detector. No envelope detector now. Envelope detector will not work here. Now what happens? If DC equal to 0, then over modulation taking place, mu may be greater than 1, then only the demodulation is synchronous detector. There is no other option. So now what is the signal finally? AC m of t cos 2 pi fct. AC m of t cos 2 pi fct. Now no denominator greater than 1, no Ka, because if no Ka, definitely the modulation will be index will be greater than 1. Therefore, now this is the modulated signal which we are having, S of t, which is equal to AC into m of t into cos 2 pi fct. Now see here, now here if I multiply it with this, now S of t, which is equal to AC am cos 2 pi fct into cos 2 pi fm into t. So S of t, which is equal to AC am by 2 into cos 2 pi fc plus fm into t plus AC am by 2 into cos 2 pi fc minus fm into t. Now this is fc plus fm upper side band, fc minus fm lower side band. Therefore two side bands. Now this is double side band. So this is double side band. Now this DC is 0. Because of this DC, this carrier component is 0. Therefore this is called as suppressed carrier. This is called as suppressed carrier. Now this is double side band suppressed carrier. This is which tone I am replacing. Therefore this is single tone. This is single tone DSBSC. This is single tone. Okay. But now this m of t keeping as it is, therefore this is nothing but multi-tone. This is multi-tone DSBSC signal and this is single tone DSBSC signal. Okay. Now see here, now this is envelope detector. Now when envelope detector is not possible, so mu greater than over modulation, synchronous detector, no Ka. Therefore, now we are expecting bandwidth is less than or not, we will see. Then the total power component is, now this is 0, only upper side band and lower side band. Okay. So this is the new modulation technique, which is nothing but, now this is nothing but double side band suppressed carrier modulated signal. This is a double side band suppressed carrier model. So most of the students are thinking that, sir, suppressed carrier is 0. When carrier is 0, no modulation. No. So here there is a side band. Side bands is nothing but the information sources, information resources. Okay. Now whenever the side bands are available, definitely that is a modulation. Modulation is done. The side bands are coming after modulation, not before modulation. Already here carrier component is available, FC, cos 2 pi fct, carrier frequency, carrier component. Okay. Now with no carrier, no modulation, nothing. Okay. Carrier is available, but previously because of this DC, one component is present, one power is present, one signal information is present. Now that is 0, so that component is 0, and there are two side bands. Information is directly available in side bands. Okay. This is two side band suppressed carrier. Okay. Note down this, and we'll see the single double side band suppressed carrier modulation technique for further. So here the maximum efficiency is 33.33%, is less because side bands will take less power. Now if you want to increase the maximum efficiency, so you want to take a side bands will take more power. Okay. But here carrier will take more power compared with the side bands. That was the efficiency decreases. Now what happened here? Now what about the carrier? No carrier, nothing. The total power is taken by the side bands. Am I not? The total power, which is nothing but upper side band power plus lower side band power, which is nothing but the total side band power. So now what is the efficiency? Now see here. Now the maximum efficiency out of total power, how much power is carried by the side bands? So whatever the total power, that itself is nothing but the sideband power. Therefore, the maximum efficiency, which is equal to 1 or 100%, because the total power, the total power, the total power carried by, the total power carried by sideband. So out of total power, the power is taken by sidebands itself. But out of total power, only 33% power is taken by sideband. 66% power is taken by carrier. That's why the efficiency decreases here. Now here the efficiency to make 100%, the total power is carried by sideband. Yes, here the power is carried by sideband, such that now efficiency is increased. To increase the efficiency, now the carrier is to be suppressed here. To increase the efficiency also, carrier is suppressed, and this is the suppressed carrier and two sideband modulation technique. Okay, no doubt. Now this is the message signal multitone. Let us assume multitone. Now S of t, which is equal to AC m of t cos 2 pi fct. Now whose Fourier transform S of f, which is equal to AC m of f minus fc plus m of f plus fc. Now whose spectral amplitude, now this will become, now this is S of f, this is in time domain and that is in frequency domain. Now spectrum, draw the spectrum. Which property? Frequency shifting property. Now here the carrier component. Now at Fc there is no impulse here. Now this is the suppressed carrier. Now this dashed line indicates the suppressed carrier. There is no impulse here. Okay. So now this 0 is at Fc. This 0 is at plus Fc. This is Fc plus omega, Fc minus omega. Now this 0 is at minus Fc. Minus Fc plus omega minus Fc minus omega. This is DSBSC spectrum. This is DSBSC spectrum. Now suppressed carrier and two sidebands. This is the upper sideband. This is lower sideband, and here the carrier is suppressed. But what about the bandwidth? The bandwidth of DSBSC signal, which is equal to 2 omega hertz, which is same as that of AM. Okay. Now whatever the bandwidth of DSBSC signal will be similar to the bandwidth of AM. But what is our intention? Our intention is to minimize the bandwidth, but unfortunately the DSBSC signal is also maintained the same bandwidth of AM. So the spectral component, the bandwidth of DSBS signal will be same as that of the AM signal. Now with respect to bandwidth, there is no improvement in DSBSC. Will be maintained the same bandwidth of AM. Okay. Now we'll see in the single tone. Bandwidth of DSBSC, which is equal to 2 omega, which is bandwidth of AM. Therefore, with respect to bandwidth, there is no improvement. There is no improvement. There is no improvement in DSBSC. Okay. So we will see in single tone. So is there any improvement in the power? Okay, because bandwidth and power are the communication resources. So with respect to bandwidth, there is no improvement in DSBSC. But what happened to the power? Power also will see. Now we'll see the single tone. Now this is S of t, which is nothing but, now what is S of t, which is AC AM cos 2 pi fm into t, cos 2 pi fm into t into cos 2 pi fc into t. Therefore, S of t, which is equal to AC AM by 2 into cos 2 pi fc plus fm into t plus AC AM by 2 into cos 2 pi fc minus fm into t. Now this is S of t. What is S of f? Now a Fourier transform of S of t, which is S of f, which is equal to AC AM by 4 into delta of f minus fc plus fm plus delta of f plus fc plus fm plus AC AM by 4 into delta of f minus fc minus fm plus delta of f minus fc So this is a impulse. Therefore, all impulse functions which is available at origin, then if you make it to 0, then you can easily get. Now this is single tone DSBSC spectrum. Now there is no suppressed carrier here. There is no impulse function at Fc. Now F equal to Fc plus Fm. F equal to Fc plus Fm. Now F equal to minus Fc minus FM minus FC minus F. Now F equal to FC minus FM. FC minus FM. Now F equal to minus FC plus FM. Minus FC plus FM. Now this is AC AM by 4. This is AC AM by 4. So this is a single tone DSBSC spectrum. Now what is the bandwidth? The bandwidth of DSBSC is 2 FM. So this is a bandwidth of DSBSC in single tone. Okay, whatever it may be, but one multi-tone is available, then single tone you can easily catch it. Okay, not. Now this is FC plus FM upper sideband, FC minus FM lower sideband. Now see here. Now what is the total power? The total power required to transmit a DSBS signal is the power taken by the upper sideband plus power taken by the lower sideband. So the total power, which is equal to AC square AM square by 8R plus RMS value AC square AM square by 8R. Therefore, which is equal to AC square AM square by 4R. So can I write like this? AC square by 2R is always unmodulated carrier power AM square by 2. So you know that the carrier power, which is equal to AC square by 2R, and power of the message signal, which is equal to AM square by 2. So this is PC into AM square by 2, which is equal to PM. So this is the total power. Now what is the total sideband power? The total sideband power, which is equal to how many sidebands? Upper sideband and lower sideband. Upper sideband power plus lower sideband power, which is equal to AC square AM square by 4R, which is equal to AC square by 2R into AM square by 2, which is equal to PC into PM. So what is the power efficiency, which we already decided? The power efficiency or modulation efficiency out of total power, how much power is carried by the sideband. Now whatever the sideband power, that will be the total power, which is equal to 1 or 100%. This is the power efficiency or modulation efficiency. Okay. Now this is the power calculation, and that is the bandwidth calculation. No. Now classroom workbook, question number 15. The carrier signal C of t equal to 10 cos 2 pi into 10 power 6 into t. A carrier signal C of t equal to 20 cos 2 pi, and a message signal m of t, which is equal to 4 cos 2 pi into 10 power 3 into t. Now this is the carrier signal and this is the message signal which is given, and the question what he is asking is these two are to generate a DSBSC signal, sketch the spectrum, calculate the bandwidth, power and efficiency. Sketch the spectrum, power, bandwidth and efficiency. So first we want to sketch the spectrum. What is the spectrum? Now this is these two are generating a DSBSC signal. Now in DSBSC signal, suppressed carrier. Now this is a suppressed carrier. Now 10 power 6 is 1000 kilo. This is kilohertz. Now FC plus FM. Now FM here is 10 kilohertz. So 1010 kilohertz. 1010 kilohertz. Kilo is all right. Now this is 1000 minus 10, 990 kilohertz. Right? This is AC AM by 4. Now S of F of DSBSC. AC AM by 4. Now see here, this is the spectrum. Now what he is asking? He is asking to find power. What is bandwidth? Bandwidth first we calculate here. The bandwidth which is equal to 1010 minus 990. Now which is nothing but 20 kilohertz. And the bandwidth is 2 FM also you can find. FM here is 10 kilohertz. 10 kilohertz means 2 into 10, 20 kilohertz. Now power, what is the total power? Now the total power which is equal to AC square by 2R into AM square by 2, which is equal to AC is 20 into 20, or you may write like this also. This is AC square by 2R, which is nothing but PC into mu square by 2. Actually here there is no Ka, so you may take mu equal to AM, because definitely there is overmodulation. Okay, so the total power which is equal to AC square by 2R 20 into 20 by 2 R equal to 1 ohm into AM. AM is, what is AM? AM which is nothing but 5 into 5 by 2. This is the total power. And this is the total power. What is the total power? .5 kilowatt. And efficiency, what is the power efficiency? Out of total power, how much power is calculated by the sideband is always suppressed carrier power efficiency is 100%. Okay. Now this is AC AM by 4. This is AC AM by 4. 20 into 5, 100 by 4 is equal to 25. Okay. Now in the same question, now he is also asking, now question number 15 is similar. Now classroom workbook question number 16. Now what is the question number 16? Now he is asking, repeat the above question by considering the message signal is this. Repeat the above question by considering the message signal 5 cos 2 pi into 10 power 4 into t plus 2 cos 2 pi into 10 power 3 into T. Now this is repeat the above question by considering the message signal m of t is this. Okay. So now this is nothing but you can easily understand. This is am1 cos 2 pi fm1 into t plus am2 cos 2 pi fm2 into t. Where a message signal consisting of multiple frequency, this is multi-tone, but this is single tone. M of t, which is equal to am cos 2 pi fm into t. Right? Now this is the single tone technique. Single tone. Now this is multi-tone signal. This is multi-tone problem. Now sketch the spectrum. Now I will sketch the spectrum first. Now Fc plus Fm1. Now what is Fc? The carry is same. Now C of t. What is C of t? 20 into cos 2 pi into 10 power 6 into t. Now this is Fc here is 100 kilohertz. Now Fc plus Fm1. Fc plus Fm1 is 1010. Now Fc plus Fm2. Now this is 1 kilohertz. Therefore, now this is 1001 kilohertz and this is 1010 kilohertz. And this one is now 999 kilohertz and this is 990 kilohertz. So the bandwidth will not affected. Now the bandwidth of DSBSC signal is 20 kilohertz. Right? Now this is SSB DSBSC spectrum, DSBSC spectrum in multi-tone. This is DSBSC spectrum in multi-tone. Now what is the total power? Now the total power here is the total power which is equal to AC square by 2R into AM1 square plus AM2 square by 2, which is nothing but we can write like this: PT, which is equal to PC into mu1 square plus mu2 square by 2. Now which is equal to the total power which is equal to PC is AC square by 2R, now which is 20 square by 2, R equal to 1 ohm into 1 by 2 into mu1 square is AM, mu equal to AM1 here. Now 5 square plus AM2 is 2 square. Now which is nothing but the total power which is 20. 2.9 kilowatt. Okay, this is a multi-tone. Okay, now whether it is a multi-tone or single tone, what is the power efficiency? Out of total power, how much power is carried by the sideband? The total power equal to sideband power. Therefore, power efficiency is 100%. Okay, no doubt. Because this voltage is less. Now this is AC. Now this is AC AM1 by 4. This is AC AM2 by 4. Now this is 25. This is 10. Now AC, which is equal to 20 into AM2. AM2 is 2. 20 into 2 by 4. So this is 10. Okay. No doubt. Now this is the single tone or multitone in any way. Okay, once if you understand multitone, because in AM in elaborate we can study what is multitone and what is single tone, so that can be implemented for any modulation technique formula. Okay, now we will see DSBSC modulator. Modulators means generation. Okay, now one simple circuit I am generating. See here, this is a product multiplayer. Now this is message signal. One input is message signal, another input is carrier signal. What is the output of this multiplayer? Now which is nothing but message signal multiplied with carrier signal. Now this is nothing but modulated signal. Now this is DSBSC modulated signal. Okay. Now this is a DSBSC modulated signal. Now this is a simple product multiplier which will generate a DSBSC signal. Therefore, this is nothing but, this is also called as product modulator. Right? Now, any modulator which will generate a DSBSC signal, now that modulator is called as a product modulator. Okay, a simple product modulator will generate a DSBSC signal when one of the input is message signal, another input is carrier signal. That is the simple way to generate a DSBSC signal, right? By using a multiplier. Now, this is called a product modulator or product multiplier, which is a simple way to generate a DSBSC signal. Okay, but now, what are the practical way to generate a DSBSC signal? There are two methods here to generate a DSBSC signal. One is balanced modulator to generate a DSBSC signal, and the second one is ring modulator. One is balanced modulator, another one is ring modulator. These are the two modulators to generate a DSBSC signal. Now, first we will see the balanced modulator. Okay. Now, here we are balancing two AM modulators. This is AM modulator 1. Now, and one carrier signal, because without carrier and message, There is no generation of AM. Now, this is AM modulator 2. Now, that is AM modulator 1 and this is AM modulator 2. Now, this is the message signal. Okay. Now, this message signal will undergo a phase shift of 180 degrees. 180 degrees phase shift. Now, this is nothing but minus m of t. Now, this is message signal. Now, this is 180 degrees phase shift. Now, these two are connected to a subtractor circuit. Now, see here. Now, what is the output of the AM modulator 1? The output of the AM modulator 1 is, this is AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT. Now, what is the output of AM modulator 2? AC cos 2 pi FCT minus AC KA m of t into cos 2 pi FCT. Now, these two are connected to a subtractor circuit. AC cos 2 FCT, AC cos 2 FCT is cancelled. Now, this is nothing but 2 KA AC m of t into cos 2 pi FCT. Now, this is passed through an amplifier circuit, amplifier of gain 1 by 2K. Now, this is 2K, 2K cancel. Now, this is Ka cancel, which is nothing but AC m of t into m of t into AC cos 2 pi FCT. Now, this is message signal multiplied with carrier signal. This is nothing but DSBSC signal. Okay, but by balancing these two AM modulators in such a way that to generate a DSBSC signal, therefore this is called as balanced modulator. Now, the balanced modulator is also called as, this balanced modulator is also called as product modulator. This is a product. The final output of this one is product of message signal and carrier, as also called as product modulator. The balanced modulator is also called as a product modulator. Now, is also called as product modulator. Therefore, the product modulator output is nothing but message signal multiplied with carrier. Therefore, this balanced modulator is also called as product modulator. And most of the practical applications, this product modulator is used, because this balanced modulator is directly available in the form of most widely used, because it is available in the form of integrated circuit. It is available directly in the form of integrated circuits. Therefore, this balanced modulator is widely used one. Okay, note down.